Last month, the world focused on the interstellar Comet 3. It passed Earth harmlessly, but almost no one noticed the real threat. A cosmic giant, 100 times larger, the Comet C 2025 R2 silently entered the solar system, concealed by the blinding light of the sun. He was discovered only after he got closest to the sun, using a cosmic hydrogen imager, and it was too late for ground telescopes to raise the alarm. In just 7 days, this monster will be closer to Earth than any major comet in history. The danger lies not in the Hollywood effect, but in what we do not see and how fragments and blind spots can lead to unforeseen consequences. How did we miss him? And are we ready for what comes next? On September 11th, 2025, a faint ultraviolet glow caught Vladimir Bezugli's attention. He analyzed data from the solar wind instrument and isotropies known as SWAN aboard the SOHO satellite, which has observed the sun's outskirts for nearly 3 decades. The image showed a hydrogen cloud expanding in an unexpected direction. For several hours, the SWAN team marked it as a possible comet. Ground telescopes rushed to confirm, but the object remained hidden behind sunlight, invisible to any optical observation on Earth. Only the ultraviolet eyes of SOHO, sensitive to hydrogen leaking from icy bodies, could reveal what lies there. By the time the discovery went through official channels, the comet had already passed its closest point to the sun. The comet discovered by Bezugli was named C 2025 R2. SWAN became the 20th comet registered by this aging space observer. Her hydrogen shells stretched for millions of kilometers, signaling a strong gas outburst and a rapid increase in brightness. For astronomers, it was both a triumph of perseverance and a reminder of evident vulnerability. Without the ultraviolet image of SWAN, the comet would have passed by unnoticed until it was far beyond perihelion. Most telescopes in the world were looking at the wrong part of the sky, blinded by the brightness of the sun. This discovery belonged to no single observer or instrument. This was the result of a system designed to capture what ground-based eyes cannot see. The question now was not only what SWAN was, but how many more giants might be hidden in the light. Sunlight creates a blind spot that has haunted astronomers for over 100 years. This area, known as the Haller effect, covers a section of the sky within about 30 degrees of the sun, where no ground-based telescope can reliably search for comets or asteroids. During these weeks, even the most advanced optical observations are powerless. Twilight conceals weak objects, atmospheric scattering makes the sky opaque, and the very geometry of Earth's orbit means that anything approaching the sun remains hidden until it moves away from the solar disk. From the end of August to mid-September 2025, Comet C 2025 R2 moved through this invisible corridor. From our perspective, the comet was immersed in daylight, its swift, bright glow completely hidden beneath the dazzling sunlight. The blind spot effect in observations is not a technological problem, but a fundamental limitation set by physics and geometry. Even the largest and brightest objects can escape notice if they approach from the wrong angle. Space instruments, such as the SWAN camera on the SOHO satellite, are rare exceptions. By observing the ultraviolet emissions of hydrogen, they can detect comets in places where ground-based eyes cannot see them. However, the SWAN camera's field of view is limited, and its outdated detectors provide only a fragmented view of the threat zone. The reality is harsh. For almost a month, a long-period comet has been racing towards the inner part of the solar system. Her emissions and dust eruptions remained invisible to all major observations on Earth. The blind spot effect not only hides weak and distant objects, it can overshadow giants until they are among us. Every object lost in the sunlight reminds us that our oversight of the cosmos has blind spots, and the next warning may only come after the danger has passed. On September 12th, 2025, the comet known as C/2025 R2 reached its perihelion, its closest point to the sun at 0.503 astronomical units, or about 75 million kilometers from the solar blaze. This moment is what long-period comets fear and astronomers await, the instant when centuries of cold storage end, giving way to a surge of solar energy capable of turning a quiet traveler into a spectacle or a victim. At this distance, solar radiation increases fourfold compared to Earth, raising surface temperatures of the core significantly above 0 degrees Celsius. Layered ice, some of which has remained untouched since prehistoric times, begins to sublimate sharply. As a result, a steam boiler effect occurs, with gases and dust erupting from weak spots and cracks, fueling the expanding comet's shell and tail. Thermal stress at perihelion can shatter old comets, especially those returning after millennia in a frozen state. For C/2025 R2, passing perihelion became both a trigger and a test. The comet's hydrogen envelope swelled, signaling a surge in water production as solar ultraviolet radiation broke down molecules leaving the surface. Observers watching the event noted a rapid increase in the comet's envelope, but the core remained shadowed, with no clear nucleus, just a bright, unresolved point at the center of activity. The sunlight still concealed direct observation, and any sudden eruption or fragmentation would remain unrecorded until the comet emerged into the dark sky. Perihelion is not just a milestone on the orbital path, but a testing stone that determines whether the comet will survive intact, shed fragments, or completely disintegrate. For C/2025 R2, what happened in those hours near the sun will determine every unpredictable behavior that follows, including eruptions, dust streams, and the possibility of debris scattering along its path. The true story of this visitor's instability began the moment he crossed the perihelion line. On October 20th, 2025, the comet designated as 2025 R2 will pass only 0.26 astronomical units from Earth, approximately 39 million kilometers, or about 101 times the distance to the Moon. For a comet of such size and brightness, this is not just close. It's a statistical anomaly. Such flybys happen once every few hundred years, not decades, but being in close proximity alone doesn't tell the whole story. The minimum distance of orbit intersection, or MOAID, measures the smallest gap between Earth's orbit and a comet's trajectory. For Comet SWAN, this value is 0.48 astronomical units, approximately 7.5 million kilometers. In cosmic terms, this is a near miss. It lies within the zone that planetary defense teams use to mark potentially hazardous objects, even if the actual risk of collision this time is 0. These figures need context. Mars, at its closest point, approaches Earth by about 56 million kilometers. The SWAN flyby passes even closer, piercing the space between our planet and the orbits of our nearest neighbors. In comparison, the comet that attracted much attention, the interstellar Comet 3, I-Atlas, never comes closer than 1.8 astronomical units, over 270 million kilometers. The approach of SWAN is more than 6 times closer, and it happens in the same week. The ticking clock does not speak of a collision. It is about what can be learned and what may be missed during these few days of the comet's closest approach. With the comet on its established trajectory, a real urgency arises from its behavior. Flashes, streams, and the possibility of unnoticed fragments become more critical as the distance decreases. MOID is not just a number on a graph. It is the dividing line between a harmless flyby and a debris flow that could sweep through the vicinity of Earth. Every kilometer matters. As October 20th approaches, astronomers hurry to gather every possible data point. The window for high-quality imaging, tracking sudden changes in brightness, and mapping surrounding dust is narrow. As soon as the SWAN moves away, the chance to study the long-period comet from such a distance will not come again for a long time. Time is running out, and the stakes depend on how much can be captured before the moment passes. The end of September brought the unexpected, which no one could have predicted. The brightness of the comet designated as 2025 R2, which was slowly decreasing after perihelion, suddenly increased by more than a full magnitude in less than half a day. Observers in the southern hemisphere were the first to notice this jump. What once appeared as a dull spot on wide-field images now rivaled the faintest stars visible to the naked eye. The comet's coma, already vast, took on a bright green hue, a clear sign of C2 and CN molecules fluorescing under the sun's ultraviolet light. This color, familiar to comet observers, signaled intense molecular activity, a chemical surge as hidden ices evaporated and rushed outward. Streams of dust and gas began to diverge from the nucleus, carving temporal arcs and lines across the coma. The geometry of these tails changed every hour, hinting at a rotating, possibly tumbling core beneath a cloud of dust. However, no telescope, even the most powerful on Earth, could resolve the core. It remained just a point against the blinding light of its own ejection. Every attempt to catch a fragment, any secondary shard or companion, ended in failure. If the ejection at the end of September shattered the core, the clues were hidden in dust, visible only to the most sensitive instruments. The unpredictability also affected the comet's light curve. Forecasts predicting that the comet SWAN would reach 6th magnitude by October were disproven by reality. The comet fluctuated between 6th and 7th magnitudes, with sharp jumps every night. Astronomy enthusiasts discussed whether they were seeing fresh emissions or just the play of sunlight on ejected dust. The truth was that no one could say for sure. Dynamically old comets, like this one, bear scars from previous encounters with the sun. Cracks, depleted reservoirs, pockets of volatile ice, waiting for the right moment to erupt. Each outburst rewrote the script, and each flash of brightness raised concerns about fragmentation. A green coma, chaotic tails, an unresolved core. All indicate a body in a state of change, its future behavior impossible to predict. For those tracking potential threats, this is a nightmare scenario. A large active comet near Earth with a history of unpredictable outbursts and no clear signs of structural integrity. The only certainty is uncertainty, and with each new image, the question becomes more acute. What if something is hidden inside this cloud of dust and light? The orbit of Comet SWAN 2025 R2 looks like a cosmic warning sign. Her path is stretched to the limit, with an eccentricity almost equal to 0 at 999 thousandths, a period of over 22,000 years, and an inclination of only 4.5 degrees above Earth's orbital plane. This geometry is not accidental. Most long-period comets move at steep angles, spending only hours or days near the ecliptic before vanishing back into the abyss. SWAN, on the contrary, lingers in Earth's track for weeks, crossing the same celestial highway traversed by planets and satellites. The likelihood of such a massive active object passing through this corridor is low, but the consequences go far beyond the numbers. Each emission, each gas jet acts like miniature engines on the core. Physics is ruthless. Sunlight strikes the surface, ice evaporates, and jets erupt, pushing out both dust and the core from predicted paths. For such an active comet, adverse forces are not just a note, but a wild trump card. Since the perihelion, astrometric data show a shift of about 1,000 kilometers from the expected trajectory, which is a direct consequence of the ejection. The effect is even more pronounced for small fragments. Radiation, pressure, and the gas effect can accelerate particles ranging from millimeters to meters along diverging trajectories, creating a diffuse stream that extends along and away from the comet's path. These particles do not disappear. For days and weeks, they spiral out, forming a wide ribbon of dust and microparticles. Earth's orbit passes through this area every year, but in 2025, the alignment will be particularly close. Even a diluted stream filled with particles too small to see can enhance the background metrics of meteoroids. For spacecraft in low Earth orbit, several additional impacts per square meter can lead to degradation of solar panels, damage to sensors, or, in rare cases, catastrophic failures. The risk lies not in a Hollywood collision, but in the quiet statistical threat of micrometeoroids, invisible until something goes wrong. Historical examples show how quickly the environment can change. Comet 73P, also known as Schwarzmann-Wachmann 3, broke apart during a close approach, and its debris rained meteors down on Earth for several years. The SWAN comet has not yet broken apart, at least for now, but its unpredictable gas emissions and unresolved nuclear issues keep that possibility alive. Each new eruption, each unpredictable movement serves as a reminder that the physics of comets does not end at their orbit. It encompasses every fragment, every speck of dust, and every spacecraft caught in the crossfire. Now the question is not only where the core will go, but also where its debris will land and how prepared we are for it. October 2025 will prepare a sky so filled that even experienced astronomers will be confused. Comet C 2025 R2 is not the only comet shining on the charts. Comet C 2025 ACE, better known as Lemon, is brightening, promising a spectacle in binoculars just as SWAN reaches its closest approach. At the same time, the Orionid meteor shower reaches its peak on the night of October 21st, sending streaks of Halley's debris across the pre-dawn sky. For the general public, this is a celestial celebration. 2 comets visible in 1 week, meteors streaking overhead, headlines full of epithets. But for those responsible for monitoring real risks, this coincidence is a double-edged sword. The spectacle draws attention upward, but also disperses it. Awareness campaigns focus on where to look and what to photograph, while subtler threats like debris flows, drifting fragments, and impacts on spacecraft take a back seat. In a week filled with cosmic attractions, the task is not only to see what is out there. One must remember which threats require vigilance and which are mere distractions. The official opening of C-2025-R2 initiated a standard reporting chain. The Small Bodies Center, JPL Horizons, then CNS. Each step in this chain depends on the data of the previous one, and each link has its problem areas. The Small Bodies Center gathers initial astrometry, often within a day after confirmation. But for comets like SWAN, the data comes with difficulty. Just a few detections after SWAN, all after perihelion, with an unresolved core. Horizons calculates preliminary orbits, but with a short observation arc, the uncertainty increases. By October 13, 2023, orbital calculations are still based only on 3 weeks of tracking, and non-gravitational forces such as emissions, jets, and subtle pushes can shift the predicted path by thousands of kilometers. CNS, responsible for risk assessment, does not even open a case if the numbers do not indicate a real threat. For long-period comets, the policy is to not intervene. This creates gaps in operational alerts and risk modeling, especially when emissions or sudden brightness spikes require manual analysis. Each orbital update requires human oversight, not only for accuracy but also to identify unpredictable factors. Considering that tools like SWAN become outdated and lose calibration, the system faces the risk of a single point of failure. One detector, decades old, monitors the blind side of the sun. The system looks reliable on paper, but late discoveries like SWAN have shown how much depends on luck, timing, and a limited number of workaholics. Small asteroids tend to slip under the radar. In 2008, TC3 was spotted only 19 hours before it burned up over Sudan. 5 years later, in 2014, asteroid AA entered the Earth's atmosphere almost without warning. Even in 2019, asteroid MO. It was discovered just a few hours before its explosion south of Puerto Rico. The lesson is simple. The angle of approach and sunlight reflections can erase days or weeks of warnings, regardless of how advanced the observation methods are. Comets add another layer of unpredictability. In 1990, Comet 37P, known as Schwarzmann-Wachmann 3, broke apart during a close approach, scattering fragments and dust that filled the skies of Earth for years. The commonality in these cases is vulnerability. Objects discovered late or unexpectedly fractured leave little time for reaction. Now the list of actions is clear. Update orbital forecast daily as new data comes in. Insist on high-quality imaging to timely capture fragments. Coordinate observations for wide-angle monitoring of dust and meteor streams. Share data on real satellite strikes and meteorological radars. Invest in telescopes aimed at the sun, not just ground observations. First and foremost, create public panels that make risk visible, not just spectacular. Each late discovery serves as a reminder. Vigilance is the only protection when blind spots in the sky are so vast. On September 11, 2025, the Comet C 2025-R2, also known as SWAN, was discovered just a day before its closest approach to the Sun, having evaded ground observations due to a blind spot. Unlike the widely discussed Comet 3 I Atlas, SWAN will pass at a distance of 0.26 astronomical units, about 39 million kilometers from Earth, on October 20, 2025. Archive data confirms the absence of an immediate collision threat, but later discoveries and unpredictable emissions highlight a systemic blind spot in our detection system. Past events such as TC3 in 2008 and AA in 2014 show that dangerous objects can be detected with minimal warning, and the breakup of Comet 37P serves as a cautionary tale about fragmentation risk. Today, the real threat lies not in the comet itself, but in the limitations of our monitoring system, especially for objects approaching the sun. As the sky becomes increasingly crowded, frequent updates, targeted observations, and investments in telescopes aimed at the sun are urgently needed. The story of Comet C 2025-R2, known as SWAN, reminds us that the next surprise may already be on its way to us, hidden in bright light and waiting to be discovered.